Hello, class. This section is 4.2, and it's called augmented matrices. So we were just learning how to solve a system of equations by graphing, by substitution and elimination or addition method. And now what if we want to solve them by a matrix? Okay, but we need to know some basic things about matrices in case you haven't looked at them or your teacher didn't cover them. So that's why I have a blank one that I'll go into the note packet in just a second. So the big idea, the first thing is a matrix. What is a matrix? It is going to be a rectangular array of numbers. Written within brackets. So it looks like this maybe, and you have numbers in it. 4, 5, 6, very inventive numbers, right? And it has brackets and it's an array of numbers. So this is what a matrix is. An element is each number inside. Okay, so an element is each number. So the matrix I just drew has 6 elements, right? This is another example of a matrix. I can have one number in it, the number 2. Still a matrix. It's pretty pointless because it's so small and has one element, but that's how it goes. Then I have dimensions of our matrix. Our dimensions go m by n, where m is your rows and n is your columns. Columns. There we go. So if I have something, it's going to go m by n, like that. This, you have like a visual of it. So the one I just did up here is going to be a 2 by 3. 2 by 3. 2 by 3. All right, so let's do an example. What if I have, doesn't matter what the numbers are, this matrix right here. What are the dimensions? Okay, 3 by 1. So it's a 3 by 1 matrix. Okay. What about the position? Of an element. Remember, an element's just one of the numbers. So the position is a double subscript, and you state the row and the column. So it's a double subscript that goes A to the IJ, where it's row, where I is row and J is columns. We have to be able to tell where that element is. So like if I have a matrix, I should be able to say the dimension, but I also need to be able to say like, where is this number specifically? Well, it is in row 1, column 1, so it would be in 1, 1. So let me list out a better matrix just for us to think this through. I'm going to call this matrix matrix A, just so you see that notation as well. Maybe this is 1, 7, 0, 4, 0, 5, -2. I want all the numbers to be different, not like the 3, 3, 3 above, because it's hard to say, hey, what position is 3 in when they're all 3s? Okay. So what position is in A11? Looks like 11, but it's not. It's 1, 1. It's row 1, column 1. So do you see that that's the number 1, right? So I'll circle that one. It's this one, right? 1, 1. Let's do a different color just because I can. What is the position 1, 2? Which number is in the position 1, 2? Well, we're still looking at 1, right? These are 1, 2, 1, 2, 3, right? So 1, 2 is -4. Okay. If I did the position A 2, 2, A 22, but not really. So we go down 2 over 2, and that's this one. So it's 0, and so forth. So I don't need to list them all. But that's how we can state our position. Okay, if we have a square matrix, then obviously your rows and columns are matching. So sometimes we use the word square matrix, and we talk about its principal diagonal. So a square matrix, let's change back to black. Maybe we'll go to black. So a square matrix has equal rows, equal columns. That's probably our easiest way to write it. Okay, rows equal columns. And our principal diagonal, we're at the end, principal diagonal. Are the numbers in the diagonal. So in my example, they will be A, E, and I. Okay, so let me show what I'm going to have. So I'm going to go A, B, C, D, E, F, G, H, I. Okay. So the principal diagonal is this right here, principal diagonal. So we can only state the principal diagonal if we have a square matrix, but it does become important as we do what we're called the augmented matrices, and we start to write our matrices as, or our systems of equations as a matrix. So everything I just did, except maybe the principal diagonal, you are supposed to have seen somewhere, but a lot of people just haven't. So that I did ask a couple questions in the homework that kind of had to do with this. So let me go ahead and open up the 4-2 notes, and we'll go this way. So if we look at what it has for row equivalent matrices, it's telling us the 3 major rules that we could do. Really, there's 2 rules, but it's saying that we can interchange any 2 rows, and we will state row 1 and row 2. We can switch them. So that's an entire row. So we have a rule that allows us to switch our rows. We have a rule that allows us to multiply a row by any number we want. Okay, just like we can multiply across an equation, we can multiply across the matrix as well. Okay, and then C says a constant multiple of one row and then add it to another row. So I actually like to think of like you can add 2 rows and replace one of the rows with that new one. So you have 2 rows, you add them together, and then one row has to stay the same, and then you replace the other row, and it doesn't matter which one. Okay. This is like basically the elimination method with a matrix. So I love matrices because they're like a puzzle and you just get to deal with the numbers. So let's go through a couple big ideas. Solve the following by augmented matrix method. So the first thing I need to do is write the augmented matrix. So what we're going to do is we're going to take what we have or what we see, and we're going to write it in matrix form. Okay, that is going to look like taking the numbers away for the first row, 2, -2, -2. Taking the numbers away from the bottom row will become 6, -2, -2. Okay, then from here, I am going to, oops, I forgot my little end bracket. I'm going to add a little dotted line here so that we can separate what the X, Y, and the number, or X1, X2 in the number. So this one has a Y. Some of our problems like to call them X1 and X2. It doesn't really matter. This row represents your X's. This row or column, excuse me, represents your Y's. And what your goal is to get ones down the diagonal right here. 1, 1, and these two numbers should be 0. And it's really the same thing you do with elimination. Okay, this is a square matrix that we kind of look at a little separate from this. So we'll get a 1 here and a 1 here, and the answer will be 1 of whatever this number is for X's. 1 will be here, and that will be the Y. So our first step is to add and get a 0 either here or here. Either way that you want to go, I can kind of look at these two, and if I multiply this by a -3, I can add and get a 0 there. So I can see if I multiply by a -3 and then I can add. So you will get better at these. And as we start them, I really just want to do each step separately. So I'm actually going to add another page so I have plenty of room. All right, and then we're going to ignore this problem because I'm going to have to keep writing in the way of that problem for now. You might need that full space as well. So the first thing I'm going to do is take and multiply -3 by row 1. And you need to write it out like this. -3 times row 1. Okay, then I'm going to replace it onto row 1. Can you just write 3 times times row 1? Sure. But we're replacing it with the arrow. That's what that means. So this becomes -6, +6, +6. Okay. Man, those are pretty equal numbers. Then the bottom stays the same because we only did something to row 1. Now I can see that we have a 6 and -6 to make the 0 here. So our goal is 1, 1, 0, 0. So here's our first 0 right here. So I'm going to add these together to get that 0. So we're going to take row 1 and we're going to add it to row 2, and we're going to replace it on row 2 so that the 0 is in the 6's place. So I'm going to do that. So when I add these two, I get 0, and that's going to replace here. Okay, then when I add these two, I get +4. And then when I add these two, I get +4. And my brackets, dotted line. Now the top stays the same. Couple ways you can always bounce back to the less multiplied one, the 2's or the 6's. Okay. So -6, 6, 6. What's the benefit of bouncing back to the 2's is those are easier numbers to deal with for the next piece. Okay, I got my first 0. Now I can finish that bottom row by dividing both by 4. I would then have the 1 where I would like it, which is right here. Okay. You did not see that yawn. I can take, yeah, let's do the 1 real quick. So I'm going to take row 2, divide it by or times it by 1/4, divide it by 4, times it by 1/4. You can state it either way. And then we're going to replace that on row 2. And I'm running out of room. I'll squish it down here. So that's going to keep -6, 6, 6. Oh, that's bad. And then 0, 1, 1. So I can already see the Y value as 1. 1Y equals 1 based on that second one being a 1. Now, my next goal is 0 here. Okay. So if this was -6, that would add there. So this time I'm going to do 2 things at once just to show you a little bit quicker. I can say times by -6 by row 2 and add it to row 1 and replace it on row 1. We're already done with row 2. So we're going to multiply, add all at the same time. So that's a legal move. And what would it look like? Well, it would look like -6 times 0 plus -6 is still -6. Okay, next row, -6 times 1 is -6. -6 plus 6 is 0. So this one's now 0. And this one's the same. -6 times 1 is -6. Plus 6 is going to give me a 0. Okay. And then we keep the 0, 1, 1 because that row's done. I don't want to mess with it. So we multiplied kind of in your head and then added. If you can't do that piece in your head, you multiply, then add separately. It's totally fine. And as the matrix get big, I have to separate it and do add, or excuse me, multiply, then add, just because I get a little lost. Okay, then from here, I need to get that -6 to be a 1. So if I divide row 1 by -6, that would then make that row and replace it on row 1. That will then make that top row have the 1 where I need it. So this becomes 1. 0 divided by anything is 0. 0 divided by anything is 0. And then we have 0, 1, 1. So we can now see our answer, x, y. So what we do is we think we go down to 1x is equal to 0. 1y is equal to 0, or 1, excuse me. So 1, 0. See how it has that on the y? And then these ones are 0. So the answer will be x equals 0, y equals 1. And that's our solution. We could list it as a point if we wanted. Okay. Oh my goodness, I am so yawning. Do we have to do 3 by 3s on this homework? Do you like that? I couldn't remember. Holy examples. I don't think so. It made me nervous that I needed to show more of them that had the 3 by 3, but I think that's the next section. Okay, that's what I get for not looking first. I haven't taught this class in a little while. Or yeah, so we'll do the yes. So sometimes this matrix method is called Gauss elimination, which is kind of a different wording a little bit, but either way, matrix method, Gauss elimination, either way you're doing this, same idea. So let's do another one. Oh goodness, I'm sorry. I'm drinking coffee. This one, let's write it as our augmented matrix. So the first row should go 1, 6, 33. Bottom one goes 6, 2, 28. Dot, dot, dot. Line, line, bracket. I mean, not line, 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 but bracket. So then this is problem 3. I did skip 2. And I'll probably skip a couple more. But then where should we start on this one? Well, we can start with making that a -6 and adding these and getting our first 0 here. So that's usually what I do is I go for my first 0 here, then I go for this 0 up there. My eyes are like watering. I'm yawning so bad. Okay, so I want a -6 times row 1. Then I'm going to add it to row 2, and I'm going to replace it on row 2 because I want the 0 here. I want this to be a -6, and I want them to add and get a 0 here. Okay, then let's do that. So I write what I'm going to do, then I do it. So -6 times this plus this is 0. So I have a 0 here. Then -6 times row 1 is -6 times 6 is -36 plus 2 is going to give me -34. I'm getting out my calculator. I ain't that good with 33. I can do 6, but I cannot do 33. So 33 on my calculator times -6 is -198 plus 28 is -170. Okay, still not that bad to do both steps in one. And then we leave 1, 6, 33. We just revert back to the same. We're only changing one row at a time. Okay, All right, so now I'm gonna see, does 170 divided by 34 go evenly? Good. Let's do it because we would like that bottom row to have smaller numbers to try to get the 0 here because we got to use both of these to get the 0. Okay, so row 2 is divisible by 34. Let's do a negative, and then that'll change everything to positive. I'm just going to kind of ignore this problem and this problem as I work down. Okay, so you should have more room than me when I write with the Apple Pencil on these note packets. It just comes through really big in Notability. So, all right, so this bottom row, the top row stays the same. And the bottom row of 0 divided by anything is 0. Negative 34 divided by negative 34 is 1. And negative 34 going into 170 goes 5 times. Okay, dot, dot, dot. Now, the 1 is way easier to work with than a negative 34. Okay, so we can see that if we times negative 6 by row 2, that would put a negative 6 here to add and get my 0 here. Okay, so then I want to add that back to row 1 and replace it on row 1. All right, so let's go ahead and do that. So negative 6 times 0 plus 1 is 1. Oops, I want this on the first one. Just kidding. Okay, I want it here, right? So let me show that. Negative 6 times 0 plus the 1 is 1. Okay, negative 6 times 1 is negative 6 plus 6 is 0. And then I'm going to steal my calculator. Oh, that's pretty easy to do. It's 3. Don't really need my calculator. So negative 6 times 5 is negative 30 plus 33 is 3. Okay, the bottom row stayed the same. Okay, take a second. What are our two solutions? What's x? 3. What's y? 5. Okay. 3 and 5. All right. So what happens if we look at like 6 and it's in the wrong form? Then you need to move this stuff around in order for it to go x, y number before you can start your matrix. So this has to go 3x minus 15y equals 15. This bottom one, I got to minus this over, so it's going to be x minus 5y equals 5. Okay, then I can go to my augmented matrix and keep doing the problem. We're going to finish this one because it has a weird solution. Okay, so go to your augmented matrix. It's going to go 3, negative 15, 15. 1, negative 5, 5. Okay, again, we call that our augmented matrix. That's why I keep saying that. Okay, then I want the 0 here. So if that's a negative 3, these would add to 0. So I am going to do negative 3 times row 2 plus row 1, replace it on row 2 because I want the 0 on the bottom left. Okay, so let's do that now. Negative 3 times that, that's going to make a 0 here. And then negative 3 times negative 5 is a positive 15, so I get a second 0 here. And then negative 3 times 5 is negative 15. I get another 0 here. I just got a whole row of zeros. Top row stayed the same. Okay, if I get a row of zeros, it's the same as if I would have got 0 equals 0 or 2 equals 2. I have many solutions. Okay, and it wants us to tell the many solutions in terms of y, right? So the form of solution is, I thought it was said it in terms of y, t. Okay, so this part's a little tricky. So we're going to kind of look back at this piece, and this is basically asking us, how do you know which solutions work? So we're going to let y equal t. Bear with me. Y is t. So I'm going to take this one because it looks like the easiest one to work with. And we're going to put the t in for y so that it goes x equals 5t plus 5. So now this is, I'm using the formula, and these are the same formula. That's why we have many solutions. If we solved for x here, we would get the exact same thing. So it doesn't matter which equation you look at. They basically just say make yt or xt, whatever, however they go with it, and then plug that into one of the equations and solve. So I would state the answer kind of weird, 5t plus 5, comma t. This is the solution. So I can't just say there are many solutions, because there are infinitely many solutions, right? Infinitely many, but really they have to meet this rule. They just aren't random solutions. They actually are on this graph. They're the same graph, and all of our points are on that graph. That's tricky. I'm not going to lie. Okay, and then some of them could end up with like 0, 0 number, and that has no solution. So a row of zeros is many solutions. A row of 0, 0 number is no solution. So let me find one. 8. 8 is going to have no solution. So let's do 8. So we're going to put it in our matrix form again. -5, 1, 12, 10, -2, -12. Okay. And I am going to try to make my first 0. So I'm like, all right, I'd like a 0 here. This looks like an easier 0 here. So if we times this by 2, we can get the 0 here first instead of this one. That's fine. So we're going to times the top row by 2, which still would make this one 0 too. But anyway, so row, oops, +2 times row 1 plus row 2. Replace it on, I don't know, we'll just do row 1. Okay, so 2 times -5 plus 10, and we're replacing it back, so that's a 0. 2 times 2 plus the -2 is 0. So 12 times 2 is 24. Plus the -12 is 12. Do you see how I did that? So -2 is 24 here, plus the -12 is +12. Okay, and then the bottom row stays the same. So I have 0, 0 number. That means no solution. We don't have to do no trick. We don't have to like no trick, but write our t and our x and y thing, because there's no solution. It's not the same as many solutions that has to meet a specific condition. Okay. There's so many. X, Y. I think we're good with that. If you need more examples, just shoot me a message, or there's more through the textbook as well. All right, hopefully that's helpful.